So we begin so this is my time, the best paper session for CC Grid 2021. This best paper selection was done by the PC co-chairs, so with Stacy Peterson and Yang-Chun Lee and myself. It was a hard task because we received a lot of good papers this year and last year. So the first presentation today will concern a paper called Characterizing Input Sensitivity in Tightly Coupled Collaborative Graph Algorithms. This paper was proposed by Jacob Hopp, Michael Kergigi, Johanna Di Girolamo, Marco Alvarez, and Apan Kassem. So the talk today will be done by Michael. Michael is a student at the University of Rhode Island. He's currently completing his Master of Science in Computer Science. He received the 2020 University Academic Excellence Award for Computer Science. His research is concerning the intersection of machine learning, computer architecture, and code. So Michael, the floor is yours. You can have the microphone and share your slides. And please, to the audience, if you want to ask questions to Michael, please send them through the Zoom chat during the talk.
Okay, great, thank you.
Thank you, Michael.
Let me see if I can pull these slides up.
For the moment, right. Yes, perfect. Yep.
Okay, thank you. So hello, everyone. Thank you for your attendance of my presentation, and also thank you to the organizers of CC Grid for allowing me this opportunity. The paper that I'll be presenting today is Characterizing Input Sensitivity in Tightly Coupled Collaborative Graph Algorithms. So graph algorithms kind of make up the core of a lot of important computational domains. This includes, for example, cybersecurity and social media data analytics, just to name a couple. And massively parallel GPU implementations of these graph algorithms work really well. But what ends up happening is that irregular graph structure causes a big difference in performance based on the structure of the graph. And I have an example here. This sort of illustrates what I'm talking about, this little chart that I have here. So on our x-axis, we have a bunch of different graphs, about 100 of them. And on our y-axis, we have the performance measured in GTEPs. And GTEPs is billions of traversed edges per second. And we have two different implementations of BFS here. One is an independent implementation and one is a collaborative implementation. The independent implementation doesn't use a unified memory system, and there's no collaboration between the CPU and the GPU. While in the collaborative implementation, it does use a unified memory system, and there's collaboration between the CPU and the GPU. And if we look at our chart here, what we see is that the performance measured in GTEPs varies drastically if we look at, say, graph number 1 here versus graph number 99. And the slope is showing that this variance is very high. And ideally, what we would like to see is that the GPU would be performing the same given graph number 1, graph number 99, graph number 50, et cetera, so that it would be a flat line. So the higher the slope that we have here, the worse that it is, because ideally we would like to have the performance maxed out on our GPU all the time. And that's for the independent implementation, this green line here. On the collaborative implementation, we see an even more drastic slope, meaning that this variation, this input sensitivity based on the graph structure, is even greater, and it poses a greater problem that we want to look at. So knowing this and kind of talking about this, we had kind of two goals going into this paper. The first goal is that we want to use machine learning techniques to sort of analyze what's going on here and figure out what's causing this issue. And the second goal is that once we've figured out sort of what are the factors playing into this and what is causing the issue, we want to create some machine learning models and basically make an auto tuner to minimize that variation by tuning software and application parameters. So now moving on to sort of how we do that. I have an overview. This diagram here takes you through a complete pipeline, start to finish, of what we did in the paper, and I'm going to walk slide by slide of what we did. And firstly, what we need to do is, on the previous slide, we talked about, okay, we measured the performance in GTEPs, but that doesn't really tell us what's going on. It tells us the performance is poor on this graph versus this graph, but we don't know what exactly is going on there. So we need to kind of define some performance criteria, their metrics, and then for these metrics, we need to actually measure it. So some specific CPU and GPU events for these metrics. And what I mean by that is some performance domains. If we look at this chart here, we define our, for example, data movement. Data movement is obviously going to be very important in a unified memory system because you're moving data over a low bandwidth, high latency channel. So that's obviously going to impact performance. And then similarly, we look at stuff like achieved parallelism and memory hierarchy utilization. And then for each of these performance domains, we have certain criteria and their metrics that we look at. So for example, for data movement, we look at data volume as the criteria, and our metric for that is copy to comp ratio. Access pattern, our metric for that is access density. And then oversubscription, and our metric for that is page remigration rate. And for all of these metrics, we have some specific CPU and GPU events that we can use to measure these so that we can actually look at the application and figure out what's going on for these metrics. So once we have these metrics, the next thing that we want to do is figure out what are the actual important metrics. What are the dominant performance criteria, and figure out like what do we actually want to look at? What is causing that input sensitivity? And the way that we do that is we construct a regression model to correlate specific inefficiencies. Our explanatory variables for that regression model are the metrics that we saw in the previous table, which are listed here again. And our target variable is the performance measured in GTEPs. So that's our response variable there. And what we find is that looking at our chart here, some of our metrics are eliminated via PCA, some are deemed insignificant, and finally, we have some metrics here that are deemed significant from our regression model. From those that are deemed significant, we have some that are not performance critical. Those are page remigration rate and branch efficiency. Some are performance critical, but their variance is low. So, there's kind of little wiggle room to work with for these metrics, and they're not highly input sensitive. And then finally, we're left with three metrics here: occupancy, access density, and register efficiency, which are performance critical, and they have a very high variance, meaning that it's input sensitive, and we could work with this and sort of using these metrics, we can tune some stuff to reduce that input sensitivity based on graph structure. So these are the three that we select for moving forward in performing some compiler and runtime optimizations and training our machine learning models for auto-tuning. So now that we have those metrics that we know are the most dominant that we want to look at, we need to expose those tunable control parameters to actually fix these inefficiencies related to these metrics. And what we do is we have some optimizations where we do data placement for access density, launch bound selection for occupancy, and register allocation for register efficiency. And we basically do some source transformations and also some compiler flags for introducing these transformations. And I have a little diagram here that shows an example of some transformations that we do. So for device placement, for example, basically we need to transform this code so that we introduce some clauses. We first look at our auto tuner here that will grab where the device placement should be, data placement, not device placement. If the data should be placed on the device or if the data should be placed on the host instead. And basically, we need to introduce some clauses into the code to manage the data structures at their allocation and deallocation sites for that. And similarly, for thread block size, the other optimization that we introduce here, the auto tuner will tell us what thread block size to use, and we could just introduce that here. And then finally, for register efficiency, to figure out our register count, the NVCC compiler allows you to specify based on a flag the max register count that you want. And so we can use that flag to basically introduce the maximum amount of registers that we want for that optimization. And with that, we introduce some notion of register eagerness being values between conservative, moderate, and aggressive for register eagerness values. A moderate register value is basically just the default. A conservative value is the default minus some set of registers, so we limit the registers there. And then an aggressive register value there is that we take the moderate value and add an amount of registers rather than taking it away. So once we've exposed those tunable control parameters, the next thing that we want to do is we can finally do some machine learning. We have a set of configurations that we can basically learn with now. And what we do is we take two different approaches for our machine learning models. The first approach that we look at is decision trees. And for our input here, we basically take a graph feature vector, we put it to our decision tree, and what we get for output is the predicted optimal configuration from the decision tree. The second approach that we look at is instead we kind of redefine the problem a little bit, and instead of classifying, predicting the optimal configuration, we change it kind of to a regression task for our MLP, where our input is changed to the graph feature vector and a configuration pair. And our MLP, now it's a regression task where it's predicting the GTEPs, that billions of traversed edges per second. And for training, we use tenfold cross-validation. And for our MLP, our hyperparameters, we look at stuff like learning rate, L2 regularization value, hidden layer sizes, etc. And for our decision trees, we train separate decision trees for different graph types, those graph types being unipartite undirected, unipartite directed, and bipartite. And once we've found the best hyperparameters for our models using that tenfold cross-validation training, we have 10% of our graphs held out for the test set that we use to perform a final evaluation and get some sort of metrics for our performance of how our models are doing for basically performing that selection of the configuration. And I have the listed configuration options here so you can get an idea of what we're looking at. So we have data placement value can either be on device or host. We have some thread block size that it can predict. And then as on the previous slide that I defined that register allocation value, it can either be the conservative, moderate, or aggressive there. So moving on to results now from those machine learning models. We define two metrics, or we look at two metrics, I should say, for evaluating our models. The first metric that we look at is percentage of optimal. This is defined as the predicted configuration performance over the optimal configuration performance, meaning that if we get a value of 1 here, the optimal configuration was predicted from our machine learning model. And the closer and closer we are to 1 means we're getting closer and closer on average to getting the most optimal configuration. The other metric that we look at is speed up over the default baseline. Speed up is basically, instead of taking the predicted configuration over the optimal configuration, instead we're taking it divided by the baseline configuration instead. So our maximum is not going to be 1. Instead, we kind of have an unbounded maximum number here, where obviously speed up, the higher the value that we get here, the better. And I should mention that this baseline is an already optimized configuration. It's not some poor configuration or anything like that. So getting a speed up over here is significant as well. And what we find from our models is that our MLP is able to achieve 96.33% of optimal on BFS and 99.4% of optimal on SSSP. And both of these are substantially above in performance. It's better than if you were to select the most frequently optimal configuration in the respective test set. And what I mean by that is, if we look at this chart here, We looked at the configurations that occurred in the test set for the most frequently optimal. So for BFS, for example, the most frequently optimal configuration is device placement is on the host. We have a 1024 thread block size and an aggressive register allocation value. And this occurs 36 times in our test set versus all of these other occurrences here. And we can look at, because one argument you can make, right, is, all right, what about instead if we just analyze that graph set and find for a particular algorithm, or maybe even for generally, some graph algorithms, what is the best, configuration for my GPU, and always use that? So like, how would that perform? And we looked into that as a metric as well to kind of provide a little bit more comparison of how our machine learning models are actually performing. And you could see that here, where if you were to select that top config for BFS, you would get 87.51% percentage of optimal, where our MLP using top one selection is able to get 94.36%, and top three selection is able to get 96.33%, which is even greater. And top one selection and top three selection, what I mean by that is top one selection, essentially what we do is with our MLP, we predict for every single possible configuration what the GTEPS is going to be from our MLP, and select the best one, what the MLP thinks is the best configuration for top one. For top three, we basically select the top three that the MLP thinks are best and select whatever performs best of that three. So essentially it gets 3 shots at predicting the optimal configuration there. And it's a similar story for SSSP as well, where we see that if we were to select the top configuration, we have 93.55% of the performance there versus 97.66 top one, and 99.4 top three for the MLP on SSSP. So it's obviously outperforming just selecting a top configuration there, and it provides some confidence that the models are performing well. Additionally, on that topic of providing confidence that the models are performing well, we wanted to show that the models are not just getting lucky, that, this isn't just some random weights that ended up performing, well on that test set or anything like that. So the way that we do that is we take those hyperparameters that were found during cross-validation training, and we basically retrain our MLP 10 times and then evaluate on the test set 10 times. And we check the variance of those 10 retrainings to see if the random weighted initializations changed anything. Ideally, you would like to see 0 variance, and even more ideally here, you would like to see that it reaches a nice, near perfect prediction rate of 1.0 here for percentage of optimal. And what we see here is for SSSP, our variance is extremely low, showing that it's generalizing to the same conclusion every time, providing more confidence that our model is actually learning the problem and mapping it to the correct solution, correct configuration, I should say. And for BFS, the variance typically is low, with only a few graphs showing any significant variation here, as we could see here. So that provides a bit more confidence in our models as well. So in conclusion here, we identified some input-sensitive performance inefficiencies. We evaluated machine learning approaches for modeling this relationship between input graph properties and performance. We demonstrated that the selected graph attributes and that performance criteria are suitable for effective machine learning models, as we could see from our results there. And for future work, it would be nice to generalize this approach that we use to a larger subset of important graph algorithms, rather than how we have it now, where it's like a specific SSSP implementation or BFS implementation. And finally, as an acknowledgement, this work was supported by the NSF through the following awards and equipment grants by IBM and NVIDIA. Thank you.
Thank you, Michael, for this very nice talk. I didn't receive any question from the Zoom chat, so audience, please send your question if you want to ask some question to Michael. So, Michael, I have two questions concerning your slide number 6 when you show your workflow. What is the time of this workflow? How long does it take for training the system?
So I think APAN can answer better because there's like two components here. For our machine learning models, training them is not too long. It took us like, I think 12 to 24 hours to get like that cross-validation training for our MLP, for example. But creating the training database is a different story of collecting all the runtime and checking what the GTEPS is for, this configuration and graph input pair, for example. So that might have been much more extensive if APAN knows for that.
Oh, okay.
Right. Yeah, I can actually answer that. So it took us about 10 days to create the database on a P100 Pascal GPU. And it took a little bit less time on the Volta GPU because, the runs were faster. But the training database, each run has to be repeated a number of times. And then we need to look at the hardware performance events. So it's a pretty time intensive operation, but that's a one-time cost that's offline. You create the training database and you're done.
Okay, so about this training time and also on the variance that you observe on slide number 8, you observe this variance of on the results, but you don't really explain why this happened. Do you have some explanation about this phenomenon?
Of these particular graphs that have a high variance? We're not sure. We didn't analyze it enough to actually give like a conclusion here. That would be something we would have to look into as well.
But is it extremely variant or I'm not sure to feel it. Yep.
So if we look at our y-axis here, basically it's a performance difference of about 20% of between our maxima and minima here for our box plot. So it's not insane, the variance, but it's ideally you'd like it near 0. For example, something like in our SSSP here, that's pretty good because it's like within, say, 2% or something like that. 20% is a little bit more of a wider gap because you're losing about 20% of percentage of optimal, meaning that you could have gotten 20% more performance there.
Okay, thank you very much.
Right, and if I could just add one more thing over there. Sorry. Yeah, so the other thing is, as Professor Feng mentioned, right? So the performance is really sensitive to these variations, right? Just a single change in the thread block size can actually have a big impact. So if our predictive model doesn't get the optimal, there's a chance that the performance that you end up with, it can be significant just because you got that one parameter wrong in certain cases.
Perfectly clear. Okay, thank you. So very nice work. I hope, Michael, you will go on a PhD on such subject now.
Thank you.
So this is the official moment of the session. Now maybe Yang Shunli, if you are around, you can put your cam on. I would like to share my screen. Apan, you can remain here. You are also concerned. I hope you can see my slide. Thank you, Yang, for joining because you were also involved in the best paper selection a lot. So this is official moment. So Michael, with your co-authors Jacob, Johanna, Marco, and Apan, you received the Best Paper Award for CC Grid 2021, and you received the third prize. This is a virtual certificate and plaque. You will receive a real one by postal service, and you'll also receive a prize of $500 for this Best Paper Award. Congratulations!
Thank you.
I think everybody is applauding now. Cheers, Raj. Congratulations, and thank you for this presentation and this very nice work that you submitted to CC Grid 2021.
Thank you.
Thank you. I stop sharing my screen.